Imagine a silent alien visitor sculpted in the fiery heart of a distant star journeying through the cold void for millennia. Now picture it sweeping past one of the most hostile planets in our solar system, leaving behind a trail of observations that shatter our expectations. In late 2025, that exact scenario unfolded. What scientists witnessed defies conventional physics, sparking a global debate that goes to the very core of our understanding of cosmic visitors. This isn't just a space rock, it's a profound mystery challenging everything we thought we knew. On November 3rd, 2025, an object from another star system dubbed 3I Atlas executed an unbelievably close flyby of Venus. The world's scientific community, already on high alert, dropped everything to watch. But what transpired during those crucial hours and the baffling data that followed contradicted almost every astronomical prediction. Some of the phenomena observed still lack any adequate explanation, igniting a fervent discussion across the scientific landscape. You might think Venus frequently receives cosmic visitors, asteroids, comets, solar winds. Our neighbouring planet has seemingly endured it all. But 3I Atlas was fundamentally different. It originated from beyond our solar system, carrying material forged in the crucible of an alien sun, a voyager that had drifted through the cosmic dark for potentially millions of years before gracing our doorstep. This wasn't just another passing speck. This was a message in a bottle from the deep cosmos, and its encounter with Venus has etched itself into the annals of space exploration. The data captured by multiple spacecraft positioned throughout the inner solar system during the flyby has ignited one of the most captivating scientific debates of the decade. This event is truly unprecedented. In all of human history, we have only ever confirmed 3 interstellar visitors. Just 3. The first Oumuamua in 2017 confounded scientists with its inexplicable acceleration and highly unusual elongated shape. Then came 2I Borisov in 2019, which behaved more conventionally like a comet. Now we have 3I Atlas, the third confirmed messenger from the stars, performing a close encounter with one of our solar system's most enigmatic planets. But it's not merely the close past that has astronomers abandoning sleep. What's generating heated, almost fiery discussions in scientific circles are the observations made after the flyby. Images captured in late November revealed strange features extending from 3I Atlas, structures that, according to conventional comet physics, simply should not exist. We're talking about incredibly straight lines projecting sideways over vast distances, temperature readings that defy all expectations for icy bodies approaching the sun, and trajectory characteristics so perplexing they've divided the scientific community into camps, each with fundamentally different interpretations of what we're witnessing. Stay with me, because in the coming minutes we will meticulously examine the verified astronomical data. We'll delve into the scientific controversy surrounding this visitor, uncover what our armada of spacecraft observed during the Venus encounter, and investigate why some respected researchers believe 3I Atlas represents something far stranger than a typical comet. We'll rigorously separate confirmed facts from speculation, present multiple scientific perspectives, and explore what this extraordinary close encounter might reveal about the true nature of interstellar travellers. When was the last time you heard about an astronomical event that prompted NASA, the European Space Agency, and astronomers from dozens of countries to simultaneously redirect their attention and pool their vast resources? When did a Harvard astrophysicist publicly question whether something traversing our solar system might not be entirely natural? That is the sheer scale of scientific mobilization and the depth of controversy we're discussing. This Venus encounter was no random cosmic lottery win. The trajectory 3I Atlas followed through the inner solar system aligned remarkably well with the orbital planes of our planets. This detail for some scientists is statistically curious, and the timing, an incredible coincidence. Multiple spacecraft happened to be ideally positioned to observe different aspects of the flyby. Europa Clipper en route to Jupiter found itself in a prime viewing spot. Hera, fresh from its asteroid mission, was in the vicinity. Soho Parker, Solar Probe and Solar Orbiter all had unprecedented viewing opportunities from their positions monitoring the Sun. Even the venerable Hubble Space Telescope was scheduled for ultraviolet spectroscopy observations. This level of coordinated observation capability is exceedingly rare. When an interstellar visitor approaches, we cannot simply dispatch a dedicated mission to intercept it. These objects move at incredible speeds, appear suddenly, and follow trajectories that our current propulsion technology struggles to match. So we must rely on whatever assets are available, gathering as much precious data as possible during their fleeting passage through our cosmic neighbourhood. For 3i Atlas's Venus encounter, we had more eyes watching than for any previous interstellar object. And what those instruments captured has generated questions that weeks later remain profoundly unanswered. Some observations aligned perfectly with scientific expectations. Others simply refuse to fit neatly into existing models of how comets behave when heated by solar radiation. And a few features have ignited a genuine scientific debate about whether our understanding of interstellar objects needs fundamental revision, or whether we are witnessing something that challenges our most basic assumptions about what truly travels between the stars. It's crucial to understand this before we delve deeper. This is not a story about sensationalized alien encounters or unfounded conspiracy theories. This is about a legitimate scientific mystery. It's about seasoned astronomers grappling with data that defies easy explanation within conventional frameworks. It's about the inherent tension between clinging to established explanations and remaining open to observations that undeniably suggest something unusual is unfolding. This is science working precisely as it should when confronted with phenomena that refuse to fit perfectly into existing boxes. The scientific method demands we follow the evidence wherever it leads, even when those paths lead to uncomfortable, perhaps even startling questions. And right now, the evidence from 3i Atlas's encounter with Venus is guiding different highly qualified scientists to profoundly different conclusions. Some see a perfectly normal comet exhibiting known behaviours that appear strange only because we're observing them for the very first time in an interstellar context. Others perceive undeniable anomalies that demand explanations beyond standard comet physics. And a bold minority are asking whether we can definitively rule out possibilities that might seem extraordinary, but which deserve rigorous investigation based on the observed data. If you are fascinated by the mysteries of space, by scientific debates unfolding in real time, by the possibility that our solar system receives visitors we're only just beginning to comprehend, then join this exploration. This isn't just about one object passing one planet. This is about humanity's rapidly expanding awareness that we inhabit a galaxy teeming with travellers from distant stellar systems. And we're just now learning how to recognise and rigorously study them. The saga of what 3i Atlas did near Venus begins with understanding what made this visitor so incredibly special to begin with, why its trajectory brought it to our neighbouring planet at this precise moment, and what scientists desperately hope to learn from this once-in-a-generation observation opportunity. Before we dive into the events at Venus, you need to grasp what makes 3i Atlas fundamentally different from anything you've ever seen streaking across the night sky. Every meteor shower, every comet you've ever heard about, every asteroid that makes headlines for passing near Earth, all of those are members of our solar system family. They were born here, formed from the same primordial disk of gas and dust that coalesced to create our sun and planets. They have been faithfully orbiting within our cosmic neighbourhood for over 4 billion years. 3i Atlas did not. It is a refugee from another star system entirely. Think about the profound implications of that. This object was shaped by conditions around a star we cannot even identify with certainty. It contains materials and compounds forged under different stellar radiation, different temperatures, different chemical environments than anything native to our solar system. For potentially millions of years, it drifted through the unimaginable vastness between stars traversing a void so enormous that light itself takes years to cross the distances involved. And then in a galaxy containing hundreds of billions of stars, its trajectory happened to intersect with our solar system. Not a collision, but a powerful gravitational interaction, a cosmic encounter that bent its path through the Sun's immense influence before sending it back out into the interstellar medium. Such visits are theoretically common. Scientists estimate that at any given moment, several interstellar objects might be passing through the distant reaches of our solar system, too faint and too far for our current telescopes to detect. But confirmed detections, those are extraordinarily rare. Spotting an interstellar visitor requires a perfect alignment of timing and sheer luck. These objects move at blistering speeds faster than anything gravitationally bound to our Sun. They appear suddenly spend mere months traversing the inner solar system, where our best telescopes can observe them and then vanish back into the cosmic dark. You need automated sky surveys relentlessly scanning the heavens, sophisticated algorithms identifying objects with unusual hyperbolic trajectories, and rapid follow-up observations to confirm their interstellar origin before the visitor races too far away to study effectively. Only 3 times in human history have we successfully identified and confirmed an object following a hyperbolic trajectory that unequivocally originated from beyond our solar system. Oumuamua arrived first tumbling through our space neighbourhood in 2017 with an elongated shape and mysterious acceleration that still fuels scientific papers and heated debate. Then came 2I Borisov in 2019, a more comet-like visitor that behaved much closer to astronomers' expectations. And now 3I Atlas III confirmed interstellar messenger, carrying with it mysteries that rival even Oumuamua's strangeness. What captivated everyone's attention wasn't just that 3I Atlas hailed from another star system, it was the specific trajectory this visitor followed as it approached the inner solar system. Interstellar objects can enter from any angle, any direction. The galaxy imposes no preferential paths. Yet 3I Atlas's trajectory aligned remarkably well with the orbital plane of our solar system's planets. Not perfectly, but close enough that some astronomers noted the alignment in their preliminary observations. Is that significant? Here's where scientific interpretation diverges. Most astronomers would tell you that with a sufficient number of interstellar visitors, some will inevitably follow trajectories that appear aligned with our planetary system purely by chance. It's a statistical expectation, not inherent evidence of anything unusual. However, a minority of scientists find the alignment curious enough to mention, especially when combined with other peculiar observations that have emerged since the Venus flyby. The true attention, however, stemmed from the unparalleled scientific opportunity this trajectory presented, because 3I Atlas's path brought it directly through the inner solar system, where multiple spacecraft and ground-based telescopes could observe it under optimal conditions. This wasn't a distant flyby through the outer solar system, where only our most powerful instruments could catch fleeting glimpses. This was a close approach that would bring the interstellar visitor near Venus, near enough that scientists could potentially detect direct interactions between the comet and the planet's thick, noxious atmosphere. NASA took notice. The European Space Agency meticulously prepared observation campaigns. Ground-based observatories worldwide scheduled precious tracking time. This was a golden chance to study interstellar material up close, to analyse the precise composition of matter from another stellar system, and to rigorously compare an interstellar comet with the comets we know intimately from our own Oort cloud and Kuiper belt. Every measurement, every spectrum, every image captured during this flyby would contribute profoundly to our understanding of what else truly exists out there in the galaxy, beyond our Sun's immediate influence. But here's what truly galvanised the scientific community into unprecedented mobilisation. The Venus encounter window coincided with favourable positions for multiple spacecraft that could contribute data from strikingly different vantage points. Europa Clipper, making its perilous journey toward Jupiter, was positioned such that it might even pass through 3I Atlas's extended ion tail. Hera spacecraft, fresh from its groundbreaking asteroid mission, had exceptional viewing opportunities. Solar observatories like SOHO Parker, Solar Probe and Solar Orbiter could track the visitor's behaviour as it approached perihelion, its closest point to the Sun. Even the iconic Hubble Space Telescope was brought into the campaign with ultraviolet spectroscopy observations planned to analyse the comet's gas emissions, seeking to understand what volatile compounds were sublimating off its surface as solar radiation heated the ancient ice. Every major space agency with assets in position wanted to capture some piece of this rare fleeting opportunity. Think about the staggering level of coordination this indicates. These aren't enthusiastic amateurs excited about a space rock. These are professional astronomers and planetary scientists acutely recognising that interstellar visitors arrive so rarely that every single observation counts. We might not see another confirmed interstellar object pass this close to a major planet for decades. This was the moment to learn everything possible while the window existed. And then, November 3rd arrived. The flyby window commenced. Instruments meticulously collected data. Scientists around the globe waited with bated breath for the downlinks and signal processing. And what emerged from that data has been sparking intense, often contentious debate ever since. Before we dissect those observations, you need to understand the environment of Venus itself. Because the planet 3i Atlas encountered is one of the strangest, most hostile environments in our entire solar system. Venus isn't just hot or cloudy. It's a world that represents an extreme, terrifying version of what planetary atmospheres can become. And when an interstellar visitor passes this close to a planet like Venus, the question isn't if something interesting happened. The burning question is whether we had the right instruments in the right positions to detect it. Venus has long been dubbed Earth's evil twin. Same approximate size, same mass, same basic composition. Yet everything that went spectacularly right for Earth went catastrophically wrong for Venus. Where Earth enjoys moderate temperatures and vast liquid water oceans, Venus boasts surface temperatures hot enough to melt lead. Where Earth offers a breathable atmosphere, Venus presents crushing atmospheric pressure and ubiquitous clouds made of corrosive sulfuric acid. It's the ultimate cautionary tale of a planetary greenhouse effect spiralling completely out of control. But here's what most people don't realise about Venus, despite being a hellish environment. At its surface, the planet's upper atmosphere is one of the most dynamic, complex atmospheric systems we have ever studied. Massive cloud patterns girdle the entire planet in just a few days, driven by winds that dwarf anything on Earth. Atmospheric waves ripple through the dense carbon dioxide envelope. Temperature variations create circulation patterns that scientists are still striving to fully comprehend. Japanese satellites like Akatsuki and various meteorological monitoring systems have been tracking Venus's atmospheric behaviour for years. Before November 2025, those observations consistently showed the patterns scientists expected. Normal planetary scale waves, consistent temperature distributions in the upper atmosphere, the sulfuric acid cloud layers maintaining their characteristic, albeit mysterious, structure. Venus was behaving like Venus always behaves, enigmatic in its intricate details but consistent in its overall macro-scale patterns. Why does this matter for our story? Because when something external influences a planetary atmosphere, its effects manifest as deviations from that established baseline behaviour. And Venus's atmosphere, despite its immense thickness and mass, is surprisingly sensitive to external influences. Changes in solar wind, intricate magnetic field interactions, even the passage of cometary material. All of these can potentially create measurable effects if they are sufficiently strong, and critically, if we are watching closely enough. Scientists understood this. That's precisely why the Venus flyby generated such profound interest. An interstellar comet passing in close proximity to a planet creates a natural, unrepeatable experiment. Will there be measurable atmospheric effects? Will the comet's extended ion tail interact even momentarily with Venus's atmospheric envelope? Will spacecraft, perfectly positioned, detect subtle yet significant changes in atmospheric composition or temperature patterns? Venus lacks a protective global magnetic field like Earth's. This makes its upper atmosphere far more vulnerable to direct interaction with charged particles and powerful plasma structures. When a comet approaches, it unfurls an extended tail of ionized gas, plasma that stretches for enormous distances behind the comet's nucleus. as the solar wind mercilessly pushes the sublimating material away from the sun. If that plasma tail happens to sweep across a planet, the interaction can create undeniable detectable effects. Earth has experienced this. Historical records document times when Earth passed through the debris streams of comets, triggering spectacular meteor showers, and even measurable, albeit subtle, changes in our upper atmosphere's chemistry. Venus cruelly lacking Earth's magnetic shield would theoretically be even more susceptible to such interactions if they occurred at sufficient intensity. The question scientists were asking before November wasn't whether interaction was possible, but whether 3I Atlas's flyby trajectory and distance would bring its plasma tail close enough to Venus to create truly measurable effects. Predictions varied wildly. Some models suggested the geometry was remarkably favourable for at least some level of interaction. Others calculated that the distances involved would render any effects too subtle to detect with our current instruments. But everyone agreed on one thing: this was absolutely worth watching. Because even if no dramatic effects occurred, the observations would still yield invaluable data about how interstellar comets behave in the inner solar system, how their plasma tails develop as they approach the sun, and how planetary atmospheres respond, or don't respond, to the passage of objects from beyond our cosmic neighbourhood. Venus, prior to November 3rd, was remarkably well characterised. Scientists possessed a comprehensive suite of baseline measurements. They knew precisely what normal looked like. This is crucial for detecting anomalies because you cannot identify something truly unusual unless you first understand what usual entails. The planet's incredibly thick atmosphere also meant that any effects from the comet encounter would need to be significant to penetrate to measurable levels. Small perturbations would be utterly swallowed by the massive atmospheric system. Only substantial, undeniable interactions would create signals strong enough to distinguish from Venus's natural turbulent variability that established a clear threshold, a minimum level of interaction required to produce detectable evidence. Some researchers even wondered if Venus's atmospheric density might ironically help preserve evidence of interaction. Unlike Earth, where atmospheric effects can dissipate quickly, Venus's thick envelope might retain signatures of external influence for longer periods. Temperature changes might persist. Compositional variations might remain detectable for days after the initial interaction. If something happened, the evidence might linger, and that's the context scientists carried into the encounter window. They possessed a baseline understanding of Venus's normal behaviour. They had instruments perfectly capable of detecting various types of atmospheric and plasma interactions. They held predictions about what might happen painstakingly derived from models of comet-planet encounters, and they were acutely aware that this was a truly unique fleeting opportunity, an interstellar visitor passing in close proximity to a major planet at a time when humanity had both the technology and the perfect positioning to observe the event. What they didn't fully anticipate, however, was how utterly complicated the interpretation of those observations would become. Because science isn't just about diligently collecting data, it is fundamentally about interpreting that data correctly. And when you're dealing with phenomena you've never directly observed before, an interstellar comet encountering Venus, the interpretation becomes a monumental challenge. November 3rd arrived with all instruments poised, all observation plans meticulously in place, all predictions painstakingly made. And then reality delivered the data. What that data showed, and more importantly what it meant, has been the subject of intense, sometimes furious discussion ever since. Because some observations matched expectations perfectly, others raise questions that still have no simple answers, and a few pieces of evidence have sparked genuine scientific controversy about what 3I Atlas truly is and what it might have done during those crucial hours near Venus. Around November the 20th, 2025, roughly 2.5 weeks after the Venus flyby images of 3I Atlas began revealing something that, according to conventional understanding of how comets behave, simply shouldn't exist. Astronomers had stacked multiple exposures to enhance faint details, a standard, robust technique for teasing out subtle structures in astronomical objects. What appeared in those meticulously processed images sparked immediate and widespread debate. Extending from 3-eye Atlas were undeniable linear features projecting sideways, almost perpendicular to the expected tail orientation. These were not the classic comet tails streaming away from the sun. These were not the dust and gas plumes that comets normally produce in all directions as their surfaces heat unevenly. These were remarkably straight lines extending perpendicular to where the main comet tail should be reaching across vast distances of space, with a geometry that struck multiple observers as profoundly unusual. Now let's be absolutely clear about something vital. Comets can produce complex structures. Fragmentation events create separate pieces that drift apart. Rotational effects can create curved features as spinning jets deposit material in spiraling patterns. Solar radiation pressure can push lightweight particles into trajectories that appear to branch away from the main tail. Experienced comet observers have witnessed plenty of unusual features over the decades, and most have straightforward explanations rooted in well-understood physics. But these features were different enough to immediately capture the attention of Harvard astronomer Avi Loeb, among others. Loeb, who has become a controversial figure in astronomy for his willingness to consider unconventional explanations for anomalous observations, quickly published his initial analysis of the images. His observations focused on specific characteristics that he found extremely difficult to reconcile with typical cometary behaviour. First was the baffling orientation. The linear features extended distinctly sideways, perpendicular to the radial direction from the Sun. Comet tails are fundamentally driven by solar radiation pressure and the solar wind, which push material radially outward from the Sun. Dust particles, gas molecules, and ionized plasma all get pushed in that same basic direction, creating the iconic tail that always points away from the Sun regardless of the comet's direction of motion. Yet here were structures extending perpendicularly to that expected fundamental orientation. Second was their remarkable straightness. When comets fragment or eject material, the resulting debris typically follows curved paths as gravity and radiation pressure combine to alter trajectories over time. A comet nucleus that's rotating will produce jets that sweep out curved patterns as the spinning surface changes the direction the jet points. These are well-documented phenomena, but the features in the 3-eye Atlas images maintained extraordinary straightness over their entire visible length. Third was the speed implication. If these linear features were separate objects moving away from the main nucleus, calculating their apparent motion speed yielded numbers that Loeb and some other analysts found noteworthy. The features appeared to be moving at velocities higher than what you'd typically expect from conventional cometary outgassing or fragmentation. Not impossibly fast, nothing violating the laws of physics, but fast enough to warrant serious notice and to question the source of energy for such velocities. And fourth, perhaps most unusually, there were baffling temperature anomalies reported in some observations of 3-eye Atlas as it approached the Sun. Instead of showing the expected temperature increases as solar radiation intensified, some measurements astonishingly suggested temperatures near absolute zero, even when the comet should have been experiencing significant solar heating. If accurate, those measurements simply do not align with how ice and rock respond to the Sun's energy. Let me emphasize something crucial here. These observations are derived from legitimate astronomical sources. The images are real. The measurements are genuine. What's in dispute isn't the data itself. It's the interpretation of what that data means. Most mainstream astronomers who have diligently examined the same evidence offer conventional explanations. The linear features could be fragments from a fragmentation event that happened to orient in that configuration by pure chance. The straightness might be an optical illusion created by our specific viewing angle, where curved features appear straight when seen edge-on. The velocity calculations could be affected by unavoidable measurement uncertainties or incorrect assumptions about the feature's actual distances from the main nucleus. The perplexing temperature readings might be instrumental artifacts, or perhaps reflect selective observation of particularly cold material. residing deep within the cometary structure. These are not dismissive explanations. They are scientifically legitimate interpretations firmly rooted in known physics and documented comet behaviour. Scientists who favour these conventional explanations are not being close-minded. They are rigorously applying the principle that extraordinary claims demand extraordinary evidence, and that familiar explanations should be thoroughly exhausted before entertaining more exotic alternatives. But Loeb and a minority of other scientists argue that while conventional explanations are individually possible, they collectively require a string of coincidences and special circumstances that in aggregate strain credibility. Yes, each individual anomaly might have a standard explanation, but when you encounter multiple unusual features simultaneously, odd orientation, unusual straightness, peculiar velocities, strange temperature readings, at some point you need to ask whether the conventional framework is being stretched beyond its reasonable limits. This is where scientific debate becomes utterly fascinating. Both sides are scrutinizing the same evidence. Both are applying rigorous analysis. Both are using the scientific method. Yet they are reaching starkly different conclusions about what the observations truly mean. That is not a failure of science. That is science working precisely as it should when confronted with ambiguous boundary-pushing data. Loeb's analysis goes further. He has calculated that if the linear features were indeed separate objects released from the main nucleus, their trajectories and speeds would be consistent with objects possessing some form of controlled motion, rather than purely ballistic trajectories. He emphasises, and this is critically important, that he is not claiming 3i Atlas is artificial. He is simply asking whether the observations allow us to definitively rule out that possibility, and arguing that the answer based on the current data is a resounding no. That distinction matters immensely. To say this is definitely alien technology is a positive claim requiring overwhelming evidence. To say we cannot definitively rule out artificial origin based on current observations is a much weaker, more cautious claim, a statement about the limits of our present knowledge rather than an assertion of exotic reality. Loeb positions himself firmly in this latter camp, arguing that scientific integrity demands we acknowledge when observations genuinely remain ambiguous. His critics, however, counter that this approach amounts to what they provocatively call clickbait astronomy, generating undue public attention and media coverage by emphasizing exotic possibilities without sufficient evidence to justify such profound speculation. They argue that Loeb's pattern, first with Oumuamua and now with 3i Atlas, represents a departure from responsible scientific communication, favouring sensational interpretations over prosaic but far more likely explanations. The debate unfortunately has at times become personal, with scientists on both sides questioning each other's motivations and methods. This is truly unfortunate as it obscures the legitimate scientific questions at the heart of the controversy. Whether or not you find Loeb's interpretations persuasive, the observations he is highlighting are real and do warrant rigorous scientific explanation. So what about Venus? Could any of these anomalous features be related to the planetary encounter that occurred just weeks earlier? Here's where speculation becomes almost unavoidable, because the connection, if any exists, is far from obvious from the available data. One hypothesis some have cautiously floated is that the Venus close approach might have triggered fragmentation through intense tidal forces or direct atmospheric interaction, and that the linear features represent fragments created during that precise encounter. This would in principle be testable by analysing whether the fragments' trajectories meticulously trace back to the Venus vicinity. But such analysis requires incredibly precise trajectory data that may not yet be available or fully processed. Another idea, far more speculative and bordering on science fiction, is that if 3i Atlas possessed any kind of internal structure or mechanisms, which remains entirely unproven and hypothetical, the gravitational interaction with Venus might have activated some kind of responsive action. This ventures deeply into pure speculation territory, but it's precisely the kind of question that inevitably arises when observations refuse to fit neatly into conventional boxes. The more conservative, widely accepted perspective is that whatever we're observing with 3I Atlas's unusual features has absolutely nothing to do with Venus at all. The timing might be purely coincidental with the linear structures developing as the comet approached perihelion and solar heating intensified, triggering outbursts or fragmentation that would have happened regardless of any planetary encounter. What we must be honest about is the observations remain profoundly ambiguous. Multiple interpretations are possible. The evidence does not yet definitively favour any single explanation to the exclusion of others. And that ambiguity is precisely what makes this situation so scientifically interesting yet frustratingly unsettled. Additional ongoing observations might in time resolve this uncertainty. If the linear features persist and continue behaving in ways demonstrably incompatible with known physics that would significantly strengthen the case for more exotic explanations, if they dissipate or evolve in ways perfectly consistent with fragmentation debris that would overwhelmingly support conventional interpretations, if future detailed analysis of the Venus encounter reveals clear, undeniable evidence of atmospheric interaction, or conversely a complete lack thereof, that might inform whether the encounter played any role in subsequent observations. But right now, in the immediate aftermath of this extraordinary flyby, we are suspended in that uncertain space where honest, dedicated scientists can look at the same data and reach vastly different conclusions, where the unsettling gap between what we observe and what we can definitively explain creates ample room for both conventional and unconventional hypotheses to coexist, neither yet proven beyond a shadow of a doubt. And that brings us to perhaps the most important question of all: what happens next? Because 3I Atlas is far from finished with its journey through our solar system. More observations are coming, better higher resolution data is being collected, and the scientific investigation into what this interstellar visitor truly is and what it did near Venus is far from over. Now let's address the question that should be lingering in your mind: did 3I Atlas actually do anything to Venus? Or was the encounter essentially a cosmic near miss with no meaningful interaction? The answer depends on what kind of interaction we're talking about, and what threshold of evidence we demand to conclude something definitively happened. Start with the most straightforward possibility: plasma interaction between the comet's ion tail and Venus's upper atmosphere. This is fundamental plasma physics. When a comet approaches the Sun, solar ultraviolet radiation ionizes some of the gas sublimating from the comet's surface. That ionized gas or plasma gets caught up by the solar wind and is relentlessly pushed away from the Sun, creating the glowing ion tail visible in many comet photographs. That tail can extend for enormous distances, potentially spanning millions of kilometers behind the comet nucleus. If Venus passed through that ion tail region, or if the tail's geometry brought ionized material into direct contact with Venus's atmospheric envelope, then charged particles from interstellar space would interact with molecules from Venus's atmosphere. This interaction would create a complex region of mixed plasma, potentially generating localized magnetic field perturbations, transient temperature variations, and subtle compositional changes detectable by the right instruments. This kind of interaction is not hypothetical. Earth has passed through cometary debris streams multiple times in recorded history. Those encounters produce spectacular meteor showers as small particles burn up in our atmosphere, and they create measurable effects in Earth's upper atmospheric chemistry that scientists can detect with specialized instruments. Venus cruelly lacking Earth's strong magnetic field that normally deflects much of the solar wind, and charged particle radiation would arguably be more susceptible to direct plasma interaction if it occurred. The burning question then is whether the specific geometry and distances involved in the November 3rd encounter would bring 3I Atlas's ion tail close enough to Venus to create truly detectable effects. Pre-flyby models offered conflicting predictions based on estimated comet outgassing rates, solar wind speeds, and the magnetic structures that form around comets, as they interact with the Sun's plasma environment. Some models suggested possible interaction. Others calculated that the distances were simply too great for significant effects. Europa Clipper's trajectory offered a potential critical way to test these predictions. If the spacecraft passed through ion-tail plasma, its instruments designed to detect charged particle environments around Jupiter would detect the plasma directly. The data from Europa Clipper during the encounter window could definitively tell scientists whether the comet's plasma structures extended far enough to reach the Venus vicinity, or whether the tail was more limited than some predictions suggested. As of the information available, NASA has not released dramatic announcements about Europa Clipper detecting clear, undeniable evidence of comet tail plasma interaction. That could mean several things. Perhaps the spacecraft didn't pass through tail regions after all. Perhaps it did, but the instruments weren't configured to capture that specific data optimally. Or perhaps the interaction occurred but was subtle enough that analysis is still vigorously ongoing. Or maybe the tail structures simply didn't extend as far as the more optimistic models predicted. The absence of immediate dramatic announcements does not in science mean nothing happened. Space science moves meticulously. Data analysis takes considerable time. Peer review demands thorough, often agonizing examination before any conclusions are published. Some of the most important discoveries in astronomy were initially ambiguous observations that required months, even years of careful analysis to properly understand. So what might Venus have experienced if plasma interaction occurred? The effects would likely be subtle and transient. Venus's massive atmosphere would not be fundamentally altered by a brief encounter with cometary plasma. We're not talking about dramatic visible changes or persistent effects that would transform the planet. Instead, think of it as a temporary perturbation, a ripple in the atmospheric system that would create measurable signals for instruments watching at the right time with the right sensitivity. Temperature variations might appear in the upper atmospheric layers where plasma interaction would occur. Compositional measurements might detect small, fleeting amounts of elements or compounds characteristic of cometary material, carbon, nitrogen, sulfur compounds appearing at altitudes where they are not normally present. Atmospheric circulation patterns might show brief localized disruptions as local heating or charged particle impacts created temporary pressure variations. All of these effects would be profoundly challenging to detect and even more challenging to definitively attribute to the comet encounter, rather than Venus's natural immense atmospheric variability. Venus's atmosphere is inherently turbulent and complex. Temperature fluctuations happen naturally. Compositional variations occur as different atmospheric layers mix. Isolating a specific signal definitively caused by external influence requires extremely careful analysis and comparison with baseline observations from periods when no encounter occurred. Here's where the scientific challenge becomes strikingly apparent. Even if instruments detected atmospheric changes during the encounter window proving causation, proving those changes were definitely caused by 3i Atlas rather than coincidental natural variability, requires meeting exceptionally high standards of evidence. You'd need to show that the observed changes were statistically significant beyond normal variation, that they occurred specifically and only during the encounter window rather than randomly before or after, and that they meticulously match the expected signature of comet atmosphere interaction rather than some other unrelated process. Meeting those rigorous standards with the currently available observations is incredibly difficult, and that difficulty is reflected in the cautious scientific literature and announcements about the encounter. We haven't seen papers definitively declaring 3i Atlas demonstrably affected Venus's atmosphere, nor have we seen definitive declarations that no interaction occurred. Instead, we're in the fascinating realm of ongoing analysis, where scientists are still tirelessly working through the data, comparing models with observations and attempting to extract clear signals from noisy measurements. But there's another more intriguing layer to this question that ventures into more speculative territory. What if the interaction between 3i Atlas and Venus involved mechanisms beyond standard plasma physics? What if, and this is where conventional scientists would urge extreme, almost frantic caution, the interstellar visitor possessed properties or capabilities that our current models simply do not account for. This is where Loeb's observations about the linear features potentially being related to the Venus encounter gain their most speculative interpretation. If, and this is a very, very large if, those features represented some kind of response or reaction to the planetary encounter, what would that imply? It would suggest internal processes within 3I Atlas, far beyond passive ice sublimation and fragmentation. It would hint at mechanisms we don't currently understand operating within or on the object itself. Most scientists would rightfully demand extraordinary undeniable evidence before entertaining such exotic hypotheses. The immense burden of proof falls squarely on those suggesting unusual mechanisms to meticulously demonstrate that conventional explanations are genuinely unequivocally inadequate, and that demonstration has not been made to the satisfaction of the broader scientific community. Yet here's what's undeniable. Something unusual appeared in observations of 3I Atlas in the weeks following the Venus flyby. Whether those features have anything at all to do with Venus, or whether they are entirely unrelated developments that happen to occur after the encounter, by pure coincidence remains utterly unresolved. The correlation in timing, while intriguing, does not prove causation, but it undeniably raises a question that deserves thorough, unbiased investigation. What would convince scientists that a genuine Venus-related effect occurred? Strong evidence would include clear, unambiguous measurements from multiple independent instruments, all showing atmospheric or compositional changes at Venus during the encounter that meticulously matched predicted signatures of comet interaction. It would include precise trajectory analysis of any fragments or features definitively showing they originated from the Venus vicinity at the exact encounter time. It would include robust theoretical modelling demonstrating exactly how the observed effects could be produced through known physics, operating precisely under the encounter conditions. Weaker evidence, what we currently have, includes interesting observations whose interpretation remains ambiguous timing correlations that might be purely coincidental, and features that could have multiple conventional explanations. That doesn't mean the observations are unimportant. It means they're not yet conclusive, and that's an honest assessment of where we scientifically stand. The Venus encounter happened. It was observed by multiple instruments from multiple vantage points. Data was collected. Subsequent observations of 3I Atlas revealed unusual features. Whether those pieces connect in a meaningful cause and effect relationship, or whether they're separate phenomena that merely happen to occur in sequence remains a profound open question. Science often operates in this space of uncertainty far longer than the public realizes. The textbook version of scientific discovery often makes it seem like observations lead directly to clear conclusions. The reality is far messier. Observations lead to multiple competing interpretations. Evidence accumulates gradually. Debates continue as scientists with different perspectives analyze data through different lenses. Eventually, sometimes quickly, sometimes over years, a consensus emerges as evidence decisively favours certain interpretations over others. We're still very much in the early phase of that process with 3I Atlas. The Venus encounter was mere weeks ago. The unusual features appeared only recently. Scientists are still rigorously analysing, still painstakingly modelling, still debating what the observations truly mean. Definitive conclusions may take months or even years to crystallise as more data becomes available and as analysis techniques continually improve. What's certain is that the encounter provided a unique opportunity to study an interstellar object under highly unusual circumstances. Whether that opportunity revealed anything truly anomalous, or whether it simply added more crucial data points to our understanding of how comets behave, is the central question driving current research. And the answer to that question will profoundly inform how we approach future interstellar visitors, what observations we prioritise, and whether our current theoretical framework for understanding these enigmatic objects is adequate, or desperately needs expansion. The Venus connection may prove to be the key that unlocks the true understanding of 3I Atlas's nature. Or it may prove to be a fascinating but ultimately coincidental timing of separate events. Either way, the scientific investigation continues relentless and unwavering, and the questions raised by this encounter will undoubtedly shape how we study the next interstellar visitor, whenever it finally arrives. No discussion of 3I Atlas would be complete without directly addressing the elephant in the astronomical room, the possibility that this interstellar visitor might be something other than a natural object. And that brings us to Avi Loeb Harvard's iconoclastic astrophysicist, who has become simultaneously one of the most prominent and most controversial voices in the discussion about interstellar objects. Loeb's involvement in this debate didn't begin with 3I Atlas. It started with Oumuamua, the first confirmed interstellar visitor, back in 2017. Oumuamua exhibited a strange unexplained acceleration as it departed our solar system, a small but measurable deviation from the trajectory that gravity alone would produce. Most astronomers attributed this to outgassing the same rocket-like effect that propels conventional comets when ice sublimates asymmetrically. Loeb, however, noted that Oumuamua showed no visible coma or tail, no clear observable evidence of the outgassing that supposedly explained its acceleration. He proposed an alternative. What if Oumuamua was being pushed by solar radiation pressure? And what if it possessed an unusually large surface area, relative to its mass like a thin sail, that would elegantly explain the acceleration without requiring invisible outgassing? And if you're going to propose a sail-like geometry, well, what naturally occurring object has that shape? Loeb didn't claim Oumuamua was artificial, but he argued the possibility couldn't be definitively ruled out and deserved serious scientific consideration. The astronomical community's reaction was swift and largely critical. Most scientists felt Loeb was prematurely jumping to exotic explanations without thoroughly exhausting conventional possibilities. They pointed out that outgassing from specific hard-to-detect volatile ices could explain Oumuamua's behaviour without requiring artificial origins. They argued that entertaining alien technology explanations without truly compelling evidence crossed the line from reasonable speculation into attention-seeking sensationalism. Loeb, however, countered that true science requires following the evidence wherever it leads, even when that direction makes people uncomfortable. He argued that dismissing possibilities without thorough unbiased investigation is just as unscientific as accepting them without sufficient evidence. And he pointed out that the history of astronomy is replete with examples where the conservative scientific consensus was eventually overturned by observations that initially seemed impossible. Now, years later, the same dynamic is playing out with 3I Atlas. Loeb has meticulously examined the new observations, the linear features, the unusual orientations, the temperature anomalies, the baffling trajectory characteristics. And he's asking the same uncomfortable question: can we definitively rule out artificial origin based on what we're now seeing? His argument isn't that 3I Atlas is definitely artificial. It's that the observations contain elements that simply do not fit comfortably within conventional comet physics, and that scientific integrity demands we acknowledge the limits of our certainty. He passionately emphasizes that he's not claiming aliens are visiting us. He's claiming that our current data doesn't yet allow us to definitively exclude that possibility, and that excluding it prematurely would be fundamentally bad science. What specific features does Loeb highlight? Start with those striking linear structures extending sideways from the main nucleus. If these are indeed separate objects released from 3I Atlas, their remarkably straight-line trajectories and apparent velocities suggest something beyond typical fragmentation physics. Loeb has calculated the immense energies required to accelerate objects to the observed speeds, and notes they exceed what normal cometary outgassing typically produces. Then there's the trajectory alignment with our solar system's planetary plane. Yes, this could be coincidental. Eventually some interstellar object will randomly happen to enter, aligned with our planetary system. But Loeb notes that the probability isn't overwhelmingly high for any random visitor, and that alignment becomes far more intriguing when combined with other unusual observations. The temperature anomalies constitute another critical piece of his argument. If 3I Atlas is showing temperatures near absolute zero, despite rapidly approaching the sun, that suggests some powerful unknown mechanism is preventing solar heating from affecting the object normally. What mechanism? Conventional explanations might involve highly reflective surfaces or specific material compositions that don't absorb solar radiation efficiently. Loeb suggests we should also consider whether artificial engineered materials might produce such baffling observations. And then there's the broader statistical argument Loeb makes. He points out that in a galaxy containing hundreds of billions of stars, many of which likely host planetary systems, the existence of technological civilizations becomes a question of staggering probability. If even a small fraction of stellar systems develop technology, and if a small fraction of those civilizations build probes or instruments to explore beyond their home systems, then the galaxy should statistically contain a substantial number of artificial objects drifting through interstellar space. If such objects exist in any significant numbers, Loeb argues, then our solar system will occasionally be visited by them, just as we are occasionally visited by natural interstellar objects like asteroids and comets. When we detect an interstellar visitor behaving unusually, shouldn't we at least rigorously investigate the possibility that we've encountered one of those artificial travellers, rather than immediately assuming it must be natural? His critics respond on multiple fronts. First, they argue that invoking artificial origins without compelling undeniable evidence violates the fundamental principle of Occam's razor, the idea that simpler explanations should be preferred over more complex ones when both fit the observations. A natural comet behaving in unusual but ultimately explainable ways is simpler than an alien probe, so that's what we should default to unless definitively forced otherwise by overwhelming evidence. Second, they point out that our understanding of comet physics is still developing, especially for interstellar comets, which we've only observed a handful of times. What appears anomalous now might simply reflect our limited experience with these exotic objects. As we observe more interstellar visitors, we will develop better, more refined models that may naturally explain the features that currently seem so strange. Third, and perhaps most pointedly, critics accuse Loeb of using sensational possibilities to generate media attention and public interest without the rigorous scientific methodology that should accompany such extraordinary claims. They suggest his approach has more to do with publicity than legitimate scientific inquiry, and that it risks damaging the credibility of astronomy by associating the field with speculative, unproven claims about aliens. Some of the criticism has become quite personal. Scientists have publicly called Loeb's work on interstellar objects clickbait and accused him of betraying scientific standards for fame and book deals. Loeb has responded that his critics are simply close-minded and unwilling to consider evidence that challenges their comfortable assumptions. This is deeply unfortunate because the personal animosity obscures what should be a productive, fascinating scientific debate. Set aside the personalities and egos for a moment. The fundamental question is entirely legitimate. When we observe interstellar objects behaving in ways we don't fully understand, what's the appropriate scientific response? Conservative scientists argue that we should meticulously exhaust natural explanations before entertaining artificial ones, and that the bar for considering artificial explanations should be exceptionally high. They are right that scientific caution is paramount, and that accepting extraordinary claims without extraordinary evidence would be poor practice. But Loeb makes a valid point that outright dismissing possibilities without investigation is equally unscientific. If we reflexively assume every anomalous observation must have a conventional explanation, and never seriously investigate alternative hypotheses, we might miss genuinely revolutionary discoveries. The productive middle ground is this treat artificial origin as a hypothesis to be rigorously tested rather than either accepted or dismissed a priori. What observations would definitively indicate artificial rather than natural origin? Design instruments and observation campaigns that could detect those unique signatures. Apply the same rigorous skeptical analysis to both conventional and unconventional hypotheses, and let the data, and only the data, determine which explanation survives scrutiny. That's not precisely what's happening in the Three-Eye Atlas debate, unfortunately. Instead, we have camps often talking past each other with Loeb highlighting anomalies, and his critics meticulously explaining them away with conventional physics, and neither side fully acknowledging the legitimate uncertainties that currently exist in our understanding. What would actually settle this intense debate? Clear, undeniable evidence is what science ultimately demands. If 3I Atlas exhibited behaviour that definitively violated known physics, if it performed manoeuvres requiring propulsion, if it emitted signals, if it demonstrated capabilities that no natural process could possibly produce, then the artificial hypothesis would gain overwhelming, irrefutable support, regardless of initial scientific skepticism. Conversely, if continued observation shows the unusual features evolving in ways fully consistent with complex but ultimately natural cometry processes, if the anomalies dissipate or resolve into well-understood phenomena, then the conventional interpretation would be resoundingly vindicated, and the artificial speculation would fade into history. Right now we're in the uncomfortable middle zone where observations are ambiguous enough that both interpretations remain marginally plausible. That ambiguity, however, won't last forever. More data is coming, better analysis will emerge, and within months or years a scientific consensus will likely form around an interpretation that commands broad acceptance. Whether that consensus validates Loeb's willingness to consider unconventional possibilities, or vindicates his critics' insistence on conventional explanations, remains to be seen. But the debate itself illustrates an important truth about science. It's not a static set of established facts. It's a dynamic, messy process of investigation that sometimes requires entertaining uncomfortable ideas to ensure we're not prematurely closing doors that should remain open. The Venus encounter adds another crucial dimension to this debate. If investigation eventually reveals that something genuinely unusual occurred during that flyby, something that cannot be explained with standard planetary comet interaction physics, then the case for 3I Atlas being more than a typical comet becomes significantly stronger. If Venus emerges as simply a coincidental timing with no meaningful connection to the object's unusual features, then conventional explanations gain further support. Either way, the scientific story continues to unfold, and the profound questions raised by this interstellar visitor ensure that astronomers will be watching closely as 3I Atlas continues its journey through our solar system, and eventually back into the interstellar void from which it came. The story of 3I Atlas and its Venus encounter is far from over. Right now, at this very moment, telescopes worldwide are relentlessly tracking this interstellar visitor as it continues its majestic journey through our solar system. Spacecraft are diligently collecting data, scientists are furiously analysing observations, and more opportunities to study this mysterious object are coming in the weeks and months ahead. December 2025 brings one of the most anticipated observations yet. The James Webb Space Telescope is scheduled to turn its unprecedented infrared capabilities toward 3I Atlas. JWST represents the most powerful infrared observatory humanity has ever constructed, capable of detecting faint thermal emissions and analysing compositions with a sensitivity that ground-based telescopes simply cannot match. What Webb observes could potentially resolve some of the current agonising ambiguities. Infrared observations unveil precise temperature distributions across an object's surface. They detect what compounds are sublimating based on their characteristic spectral signatures. They can identify complex organic molecules, water ice, carbon dioxide, methane, and dozens of other materials by their unique infrared fingerprints. If 3I Atlas is a conventional comet, JWST should see compositional signatures consistent with known solar system comets, or perhaps reveal truly exotic compounds characteristic of formation in a vastly different stellar environment. If something stranger is occurring, JWST might detect thermal patterns that defy expectations for solar heating of passive ice and rock. It might even see compositional anomalies that directly challenge our understanding of what interstellar objects should be made of. Or it might confirm conventional composition and thermal behaviour, strengthening the case that 3I Atlas is an unusual-looking but ultimately natural comet. Hubble continues its observation campaign as well. Ultraviolet spectroscopy meticulously tracks gas emissions as the comet's activity level changes with its distance from the Sun. Every spectrum captured adds to the massive data set scientists will use to model what's truly happening to this object. Over time, patterns will emerge. Outgassing rates might show expected changes as solar heating varies, or they might reveal alarming irregularities that demand new explanations. Ground-based telescopes worldwide are contributing observations as 3i Atlas moves through the constellations of Virgo and Leo in the coming months. Professional observatories with colossal mirrors can capture detailed images meticulously showing how those controversial linear features evolve over time. Even amateur astronomers with sophisticated equipment are tracking the comet, creating a distributed observation network that ensures continuous monitoring, even when professional facilities are scheduled for other critical projects. This kind of sustained observation campaign is relatively rare. Most comets simply don't warrant such intensive scrutiny. But 3i Atlas's interstellar origin and unusual features have elevated it to a special status where every available instrument that can contribute data is being utilised to maximum effect. The brightness predictions suggest 3i Atlas will remain observable for months as it recedes from the Sun, though it will gradually fade as solar heating decreases and the comet's activity level drops. The window for truly detailed observation is limited. Within several months, the object will become too faint for all but the largest telescopes to study effectively. That makes the current period absolutely crucial. This is our best, most opportune chance to gather comprehensive data before 3i Atlas fades into cosmic obscurity. But there's another encounter coming that has scientists particularly intrigued. In March 2026, 3i Atlas will make its closest approach to Jupiter. Now it won't be nearly as close to Jupiter as it passed Venus. The geometry is different, the distance is significantly larger. But Jupiter's massive gravitational field and complex magnetosphere create an environment where even distant encounters can produce observable effects. Jupiter is surrounded by intense radiation belts, powerful magnetic field structures, and a vast system of moons that provide multiple vantage points for observation. The Juno spacecraft currently orbiting Jupiter might have unprecedented opportunities to observe 3i Atlas from its unique position. Ground-based telescopes watching Jupiter could potentially detect any subtle interactions between the comet and Jupiter's extended magnetosphere. What scientists will be relentlessly looking for is consistency. Does 3i Atlas continue exhibiting the unusual features observed after the Venus encounter, or do those features dissipate and disappear? Does the object's trajectory remain perfectly consistent with gravitational dynamics, or do any additional non-gravitational accelerations appear? Does continued spectroscopic observation reveal anything unexpected about its composition or outgassing patterns? These ongoing observations serve multiple vital purposes. They test competing hypotheses about what 3i Atlas is and how it's behaving. They provide crucial data that will inform how we approach future interstellar visitors. And they contribute to the rapidly growing data set of interstellar object observations that will eventually allow scientists to understand how typical or atypical each individual visitor truly turns out to be. One crucial aspect of modern astronomy is that observations aren't kept secret. Scientists publish their data, share their findings through papers and conferences, and make measurements available to the broader research community. That means independent teams can analyse the same observations, rigorously check each other's conclusions, and identify errors or alternative interpretations that a single research group might miss. This collaborative, transparent process is how scientific consensus eventually emerges. It's not about one charismatic scientist convincing everyone else to accept their interpretation. It's about multiple independent researchers meticulously examining evidence, testing hypotheses, and gradually converging on explanations that best fit the totality of available data. For 3i Atlas, that process is vigorously ongoing. Papers are being written analysing various aspects of the encounter and subsequent observations. Conferences will feature presentations hotly debating interpretations. Peer reviewers will scrutinise claims for weaknesses or unwarranted assumptions. It's messy and slow, but it's precisely how science separates reliable conclusions from preliminary speculation. What should you watch for in the coming months as this story continues to dramatically develop? First, look for any announcements about JWST observations and what they reveal about composition and thermal behaviour. Those could be game changers for understanding what 3i Atlas actually is. Second, pay acute attention to whether the controversial linear features persist, evolve, or disappear. Their ultimate fate will profoundly inform whether they represent genuine anomalies, requiring exotic explanation, or transient structures that ultimately fit within conventional comet physics. Third, watch for any definitive evidence emerging about the Venus encounter itself. Did Europa Clipper or other spacecraft detect clear, unambiguous signals of atmospheric interaction? Have scientists analysing Venus observation data found any atmospheric changes precisely corresponding to the flyby timing? Positive findings would elevate the encounter from an interesting coincidence to a meaningful, impactful event. And fourth, keep a close eye on the ongoing Loeb controversy. Will additional observations vindicate his willingness to consider unconventional interpretations, or will they staunchly support his critics' insistence that conventional explanations suffice? Science has a powerful way of resolving these debates eventually, even when the personalities involved make the process far more dramatic than strictly necessary. The ultimate fate of 3i Atlas is already determined by the immutable laws of physics. After passing Jupiter in March, it will continue outward, eventually leaving our solar system entirely and majestically, returning to the interstellar medium from which it came. Within years, it will become too distant for even our best telescopes to detect. It will become once again just another unseen traveller in the vast galactic ecosystem of objects, drifting silently between the stars. But the invaluable data we collect during its brief, spectacular passage through our neighbourhood will remain. That data will be analysed and reanalysed for years, tirelessly contributing to our understanding of what truly exists beyond our solar system and what we should expect from future interstellar visitors. Every measurement adds to our collective knowledge. Every observation informs our ever-evolving models. Every interstellar object we successfully study brings us incrementally closer to understanding the vast complex galaxy we inhabit. And that brings us to the final profound question. What does all of this mean? Why should you, the curious observer, care about an icy rock from another star system that briefly passed our neighbouring planet? What profound significance does this encounter hold beyond the immediate scientific curiosity it undeniably generates? Step back for a moment from the intricate details about trajectories and plasma interactions and heated scientific controversies. Look at the bigger, breathtaking picture of what's actually happening here. For the very first time in human history, we are developing the unprecedented capability to routinely detect, track, and meticulously study objects that originated in other stellar systems. Think about the staggering implications of that. For all of human existence until just a few years ago, everything we studied in the sky either unequivocally belonged to our solar system or was so astronomically distant that we could only observe it passively with light that had travelled for years or millennia to reach us. Planets, moons, asteroids, comets, all cherished members of our local cosmic family. Stars, galaxies, nebulae. Beautiful, yes, but untouchably remote. Interstellar objects occupy a unique, almost mystical middle ground. They're not from here yet, they pass close enough that our instruments can analyse them in astonishing detail. They are true travellers from distant places carrying invaluable information about environments and processes occurring around other stars. They are like messages in bottles thrown into the boundless galactic ocean, washing up on our shore for brief precious moments before drifting away again. Oumuamua was the first confirmed bottle we found. 2I Borisov was the second. Now 3I Atlas is the third. Each one taught us something fundamentally different. Each one revealed that interstellar visitors come in varieties we hadn't even anticipated. Each one raised profound questions about how typical our solar system truly is, compared to the wider galactic environment where these objects originally formed. And here's what's truly remarkable. We're detecting more of them not because more are arriving, but because our technology is rapidly getting better. The galaxy has always been filled with these silent travellers. Countless objects drift through interstellar space, most following trajectories that never bring them near any star system. others occasionally passing through stellar neighbourhoods like ours. They've been there all along. We simply couldn't see them until we built automated sky surveys sensitive enough to spot their faint fleeting signatures against the background stars. That technological capability is accelerating at an incredible pace. New surveys coming online in the next decade will detect interstellar visitors far more frequently. What once seemed like rare, once-in-a-lifetime cosmic events will become routine, almost daily observations. We'll build statistical samples large enough to finally understand how common different types of interstellar objects truly are. We'll learn whether our solar system's comets and asteroids are typical, or whether we're the peculiar outliers in a galaxy teeming with diverse varieties. The Venus encounter adds scientific value far beyond just the flyby itself. It's the first time we've observed an interstellar object having a close encounter with a major planet, while we had the instruments and positioning to potentially detect interactions. That's unprecedented. Even if the encounter produced no dramatic effects, the observations meticulously establish baselines for what doesn't happen when an interstellar comet passes a planet. If effects did occur, if Venus's atmosphere responded measurably to 3I Atlas's passage, then we've witnessed the first confirmed interaction between interstellar material and a solar system planet. That's fundamentally significant for understanding how material migrates between stellar systems, how planetary atmospheres respond to external influences, and what kinds of exchange processes might occur when interstellar visitors pass through potentially inhabited systems. Think about the profound implications in the context of life and planetary habitability. Earth has certainly been visited by interstellar objects throughout its history, just as Venus was potentially visited by 3I Atlas. We weren't watching for most of that history, but the visits undeniably happened. Did any of those ancient encounters deliver materials to Earth's nascent atmosphere? Could complex organic compounds from other stellar systems have contributed to the crucial chemical inventory from which life eventually emerged? These are not wild speculations. Scientists seriously study panspermia hypotheses, the idea that life's building blocks or even simple organisms might be transported between stellar systems via interstellar objects. Most experts consider it unlikely that life itself travels this way, but the transport of complex organic molecules is entirely plausible. Comets are known to contain rich organic chemistry. Interstellar comets carry organics formed under different stellar conditions. When they encounter planets, some material exchange could in theory occur. Whether or not 3I Atlas contributed anything significant to Venus's atmospheric chemistry, the principle holds. Interstellar visitors have been mixing materials between stellar systems for billions of years. Our solar system's chemical inventory isn't purely local. It includes contributions from interstellar space delivered by objects like 3I Atlas. Now let's address the artificial question one more time, because it matters immensely to the bigger picture. If, and this remains highly speculative, if any interstellar visitors turn out to be artificial rather than natural, what would that mean? It would mean we are unequivocally not alone in the galaxy. It would mean other technological civilizations exist and have developed the astonishing capability to send instruments or probes beyond their home systems. It would mean the galaxy contains not just natural processes, but also the deliberate products of intelligence and engineering. That would be the single most profound discovery in human history. It would reframe our understanding of our place in the universe more dramatically than any previous scientific revolution. It would raise fundamental questions about why we are being visited where the communication is possible, and how humanity should respond to the knowledge that we share the galaxy with others. But here's the crucial caveat. We don't have evidence that this is the case, not yet. The ambiguous observations of 3I Atlas, like the earlier ambiguities of Oumuamua, do not constitute proof of artificial origin. They constitute interesting, perplexing data that hasn't been definitively explained yet. There's a vast critical difference between not yet explained and artificial. Science rigorously requires we maintain that distinction. Being open to possibilities isn't the same as accepting them without sufficient evidence. And right now, the overwhelming evidence does not support concluding that 3I Atlas is anything other than a natural object, even if it's a natural object exhibiting behaviours we don't yet fully understand. So whether 3I Atlas is natural or artificial, and the overwhelming probability favours natural, the encounter matters. It matters because it dramatically advances our observational capabilities and our understanding of what truly travels through the galaxy. It matters because it demonstrates that we can mobilise coordinated observation campaigns when rare, invaluable opportunities arise. It matters because the intense scientific debates it's generating will refine our methods for interpreting ambiguous observations. And it matters because it starkly reminds us that we live in a dynamic, interconnected galaxy, where our solar system isn't an isolated island. We're part of a vast ecosystem where materials and objects move freely between stellar systems, where encounters like the Venus flyby happen regularly on cosmic timescales, and where our increasing technological sophistication allows us to observe and study processes that our ancestors could never have even imagined. Every interstellar visitor we detect profoundly expands our cosmic perspective. We're no longer limited to studying just our own solar system's inventory. We're beginning to sample what exists beyond to compare different stellar environments to understand how the galaxy's chemical and physical evolution creates the astonishing diversity of objects we are now discovering. 3I Atlas won't be the last mysterious visitor. It won't be the last object that generates scientific debate and ambiguous observations. As detection capabilities inevitably improve, we'll encounter interstellar travellers regularly. Some clearly conventional, some puzzlingly unusual, and perhaps eventually one that provides definitive, irrefutable evidence of something truly extraordinary. But regardless of whether extraordinary discoveries lie ahead, the ordinary discoveries are invaluable too. Every confirmed interstellar object adds profoundly to our understanding. Every successful observation campaign demonstrates our growing capability to study these cosmic travellers. Every scientific debate about interpretation refines our methods and humbly reminds us that the universe still holds countless mysteries we are tirelessly working to comprehend. Venus has been visited before by spacecraft we built and sent to explore our neighbouring planet. But it had never, at least not in the brief period we've been watching, been visited by something from another star. What that visit revealed, or didn't reveal, will be debated for years. The data will be analysed and reanalysed. Competing interpretations will be tested against continued observations, and eventually a scientific consensus will emerge about what 3I Atlas truly was and what its encounter with Venus actually meant. Until then, we have the immense privilege of witnessing science in action. We see the messy, exhilarating process of investigation, the profound uncertainty that precedes clarity, the intense debates that eventually resolve into understanding. We're living through a moment when humanity's cosmic awareness is rapidly expanding, when we're transitioning from mere observers of our local neighbourhood to dedicated students of the broader galaxy. And that's why this story matters, not just because one specific comet passed one specific planet, but because that event represents humanity reaching a new threshold of capability and awareness. We're no longer confined to wondering what might exist beyond our solar system. We're beginning to observe it directly, to study it rigorously, and to understand our true place within the vast dynamic galactic community of matter and motion. The encounter between 3I Atlas and Venus is just one compelling chapter in that larger unfolding story, but it's a chapter worth paying acute attention to, because it's a tantalising glimpse of the discoveries and profound questions that await as we continue learning to recognise and understand the travellers from beyond who pass through our cosmic neighbourhood. Some will be mundane, some will be fascinating, and perhaps someday one will be extraordinary. Until then, we watch, we measure, we debate, and we learn. That's how science advances. That's how humanity expands its understanding. And that's why what happened at Venus on November 3rd, 2025 deserves your unwavering attention and your boundless curiosity.